Alright guys, now we're going to begin our journey into the world of perturbation theory. Now, in your quantum mechanics career, you might not think perturbation theory is important, at least not at this level, but the tools from perturbation theory are going to be essential when solving real problems. Because in reality, you don't have a simple harmonic oscillator, and you don't have a basic momentum eigenstates. There's always going to be some kind of perturbation, and we're going to have to deal with that. So the main essence, so right now we're going to start doing time-independent perturbation theory. So let me just write that. Time-independent perturbation theory. Alright, and then after this we're going to do time-independent degenerate perturbation theory. But for now, let's just do the basic case. So perturbation theory, what it boils down to is you have some Hamiltonian, and this Hamiltonian is going to be a combination of some original Hamiltonian, H naught. This is the unperturbed Hamiltonian, and what this does is basically the original state. It could be a simple harmonic oscillator, it could be the simple two-state system, it could be anything you want, just the unperturbed state. And then what we're going to do is we're going to add, let me pick a different color here, we're going to add a perturbation. And this perturbation, we're going to write lambda times delta H. Okay? And this lambda parameter can go from 0 to 1. So basically it says, lambda basically says how much perturbation do we have. If lambda is around 0, we don't have a lot of perturbation. If lambda is already at 1, then we have our full perturbation. And delta H is our perturbation, okay? So as an example, for a simple harmonic oscillator system, we have something like, so example, okay, and just to make it concrete, our initial unperturbed Hamiltonian can be something like 1/2 m omega squared, x squared. And then, so this is the simple harmonic oscillator, and then we can have a perturbation that's like, I don't know, it could be something like V naught units of energy times x to the fourth over d to the fourth. So this is basic perturbation, and we want to find the main goal of perturbation theory is to find the corrected eigenstates. So this is what I was going to get into next here. For the unperturbed Hamiltonian, we can solve this because it's a base case, right? So we're going to know the eigenstates of this unperturbed Hamiltonian, and we're going to call these eigenstates n0. And n could be whatever, right? N just describes the state of the system. If n equals 1, we're in the first state. If n equals 0, we're in the ground state, okay? So these are the eigenstates of the unperturbed Hamiltonian. And then when we add the perturbation, the eigenstates are going to be, now they're going to be a function of lambda. And this is the very important point. We can expand this corrected eigenstate in terms of the original eigenstate. And then we're going to add these perturbations. And the first one is going to be plus lambda times the first order correction, right? And plus lambda squared times the second order correction plus dot dot dot. So all we're doing here is we're saying that the new eigenstates with this perturbed Hamiltonian, the inclusion of it, we're going to expand it as a Taylor series around the unperturbed Hamiltonian in powers of lambda. So for example, this would be the first order state correction, this would be the second order state correction, and so on and so forth. Similarly, for the energies, remember from the Schrodinger equation for the unperturbed state, we had H0 times acting on N0 is nothing more than En0, right? What this means is that it's the nth energy to 0th order, so unperturbed. En0 times N0. This is just the Schrodinger equation. And so the energies, the corrected energies, will follow the same pattern. It's going to be the proper energies are going to be Taylor expanded in terms of 0 energy, and then we're going to have to add plus lambda times En1, right, plus lambda squared times En2 plus dot dot dot. Okay? So we're just expanding it, and this would be the first order energy correction, this would be the second order energy correction. Okay? That's all it is. And perturbation theory is, what are these corrections? And also later we're going to talk a little bit about convergence. Does this series converge? Okay? So I'm going to be honest, a lot of this is bookkeeping, so you have to know what all the variables mean. But if you can understand that, then we should have a pretty good time here. And it's pretty interesting too, once you start doing it. Okay, so this is what we're going to do. We have the original Hamiltonian and the original eigenstates satisfy this Schrodinger equation, right? H0 times N0 equals En0 times N0. This is just the regular Schrodinger equation. And now so this is for the unperturbed states. Unperturbed states. And then the corrected energies and states are going to satisfy this Schrodinger equation. H of lambda times n lambda. This means the corrected eigenstate after the perturbation equals En lambda on n lambda. Okay? So this is for the corrected states. Alright? So how are we going to do this? Well, it's actually pretty simple. What we're going to do is just expand this guy out. So let's expand. Now let me pick a nice color here. Maybe I'll go with blue. So, okay, what's H lambda? H lambda is nothing but H0 plus lambda times delta H, right? And then this is going to be acting on this whole N0 plus lambda N1 plus lambda N2. I'll just leave it to first order. Plus dot dot dot. Okay? Equals En0 plus lambda En1 plus dot dot dot. Okay? And again, acting on N0 plus lambda N1 plus dot dot dot. Okay. And now what we're going to do is we're going to collect like terms. I mean, we're going to collect the same powers of lambda. So for example, let me pick a different color here. For lambda 0, the 0th order term is just going to be, well, we have this guy acting on this guy. There's no lambda there. So I have H0 acting on N0. Okay. Is there anything else here? Nope. Everything else has order lambda. And then here we have En0 and N0. Okay. So I'll just pull that to the other side. Minus En0 N0 equals 0. Simplifying this a bit, we just get H0 minus En0, whole thing acting on N0 equals 0. And this should be, technically there should be an identity here because this is a matrix acting on a vector, but we'll go with this. So this is the 0th order state. And this, honestly, if you take a moment to stare at it, this is trivially satisfied, right? This is exactly this, right? This is just a Schrodinger equation for the unperturbed state. So this doesn't give us any new information. Okay, but now let's look at the first order energy correction. And immediately we'll see that we have H0 times lambda 1 N1, sorry. And then we have also delta H acting on N0, right? I'll make that a squiggly line. We have delta H acting on N0. What else do we have? We have En0, N1, right? And we also have, here we go, En1, and N0. Okay, so now on the next line over here, I'm just gonna collect all those terms. So let me make myself some space real quick. Alright, so lambda 1. What we're going to get is, you can look back, pause the video if you want, but it's going to be H0 minus En0, all acting on N1, equals, what was it? I think it is, hold on a second. It's going to be En1 minus delta H acting on N0. Okay, now this is something we can work with because we have the first order energy correction here. So what can we do? Well, this is exactly what we're going to do. Remember, N is just a single eigenstate. I can also say if I want M0, which refers to another eigenstate where M is not equal to N, right? You can think of it as we have, let's say we have N amount of states, right? N states, N eigenstates. Then this state we can call maybe N0, and this one we can call M0. It just refers to a particular state. I can call it whatever I want, P0, right? And all these, N will vary, N goes from, what is it? Let's say 0 to N, right? That's not the best notation, but it's N is equal to 0, 1, 2, blah, 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 to N, right? It just refers to a single eigenstate. So what I want to do is, let's attack this guy, attack this equation from the left with N0, okay? And what does that get us? Well, okay, right now I'll just do it really, really slowly because we're just starting to understand what this is. But later I'll make it much more quick. So let's act on it. I'm going to have N0 and then H0 minus En0 acting on N1 equals N0, and then I have En1 minus delta H acting on N0. Okay, so now let's look. Let us look what's happening here. First things first, we can act H0 on N0 because H is Hermitian, right? It is the Hamiltonian, so it's Hermitian. So H0 acting on N0 will give you nothing more than En0 and then the same state N0. This is just a Schrodinger equation, right? But in the bra space. And now notice, this En0 will cancel out with this En0. So this whole term is 0. Okay, that's cool, that's cool. So 0 equals. Now let's look at this. En1 is just a number, right? So we can pull it out of this inner product. And then we're just going to be left with N0 and N0. Oh, and I forgot to mention this, but the eigenstates we assume to be normalized. So that means N0 and then the inner product of M0 is always going to be Kronecker delta, right? And Kronecker delta just means it's 1 if they're the same, and it's 0 if they're not the same. So 1 if they're the same means that they're if they're the same, that means they're normalized, and if they're different, that means they're orthogonal. So we assume the eigenstates are, this is actually pretty important, so I'm going to write it down. Orthogonal, so this guy is 0 if they're different, and normalized. Okay? These are the two assumptions that we have. And these are fairly reasonable assumptions. Okay. Anyways, N0 is 1. So we just get En1. And then we have minus the matrix element of delta H. Okay. But now look at this. We have our first order energy corrections, right? En1 equals N0 delta H N0. Booyah! And actually this comes up so often that I'm gonna define it to be delta H N N. Okay? And this is a pretty good notation. N refers to this guy, and the other N refers to that guy. So this, we did it. You might not think we did much, but we actually did it. We found the first order energy corrections. So this is pretty important, so let me box it real quick. Okay, awesome. I'll call this equation 1. Those are the first order energy corrections. We did what we wanted to do. We found the first order energy corrections. Okay, now let's try to find the second, we can find the second order, but first let's find the first order state corrections. Okay, now how are we going to do this? We're going to do this by well, let me just rewrite it again. H0 minus, what was it, En0, and then we have N1 equals En1 minus delta H N0. Okay, and now what I'm going to do is I'm going to act from the left with another state, M0 and M0. Okay? And remember, M does not equal to N. So these are two different eigenstates. Okay? So, first things first. Let me pick a different color here. H0 acting on M0. What is that going to give us? Well, it's going to give us EM0 times M0, right? Again, Schrodinger equation. And then we're going to have, so this simplifies to EM0 minus En0, and then the matrix element M0, N1. Okay? All this means is the component of the corrected state, the first order correction, in the basis M0. Okay? I mean, not really in the basis, but along M0. Okay? It's just the projection. Okay, anyways. So, this term, this first one will be 0, because En is just a scalar, gets pulled outside, and then M0, N0 equals 0, right? M0, N0 equals 0. They're orthogonal, remember? Okay, so we're just left with, whoops, there should be a parenthesis here, my bad. We're just left with negative M0 delta H N0. And if you remember from our notation, this is exactly negative delta H Mn, right? M for the left, N for the right. So, solving for the component along M0 in the corrected eigenstate equals negative delta H Mn over EM0 minus En0. Okay, great. You could already see something interesting. What happens when EM0 equals En0, right? This is interesting. So you can already see that degenerate perturbation theory is going to be much different, because in degenerate perturbation theory, you guys know that we can have the same energies for different eigenstates. So this is going to be a problem. But let's not worry about that right now. Alright, so here I've just made a new page and I rewrote the result that we just obtained. So what does this mean? Well, as I explained, this is the component of the first order correction along the M state. Okay? If we want to find the total, let me write this in black. If we want to find the actual state, right, we're going to have to sum over all basis states, right? So it's going to be the sum over M of M0, 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 and 1. And all I did here was I just invoked the identity. And if you guys remember from your previous quantum mechanics, this is just the identity. The sum over M of M0, M0 is just 1, right? Identity. Okay? So I just put the identity here. But really what this means is that I'm summing over all energy eigenstates, and I'm taking the component along each energy eigenstate. In terms of vectors, what this means is that a vector can be written as the sum over all coordinates of Vi times Ei. So for example, it would be like Vx, Ex, where Ex is the unit vector, plus Vy, Ey. It's just the components, right? And you can make this a clear analogy here. It's just the components multiplied by the unit vectors. And in this case, the unit vectors are just the basis states. Alright? Anyways, one little thing is that this should be the sum of M does not equal to N. Because when M equals N, we're going to have an n0 here, right? And n0 and 1 equals 0, right? n0 and 1 equals 0. Okay, so let's do it. Get a nice color here. All we have to do is just plug in this result, and we're on our way. So n1 equals negative sum m does not equal to n of delta h mn over em0 minus en0 times m0. This is it. This is our first order state correction. Let's box that guy. Call this equation 2. And I think that's what I'm going to leave it at right now. I'm already running a bit on time, 20 minutes. I don't want to make these videos too long, but I want to explain it very, very fundamentally. So this is our first order state correction, and our first order energy correction, just to reiterate, was En1. First order energy correction is just negative delta H. Oops, not negative. Sorry. It's just delta H and N. That was equation 1. So we found the first order energy correction and the first order state correction. In the next video, let's do some examples, okay, to solidify these concepts, because this might seem vague to you still. Okay, so let's do some examples.